I'm in Minitab and I'm having a look at the What is a Disease survey dataset, and we're going to have a look at some bar charts and doing a chi-squared test of independence. Now, what we've got here are 4 different groups of people: lay people, doctors, nurses and members of parliament were asked if a whole list of conditions were a disease or not. I don't have the exact wording of the question, you have to go to the original paper for that. And the one that I want to look at quickly is just the baldness. I think that's a nice, interesting, they're all interesting, but we'll stick with the baldness. So what I have done is I've recoded this group column into another column with labels just to make it easier to read. So you can see here the group name, lay people, doctors, nurses and members of parliament are also in there. And then if I go back to baldness, you might want to just change the title to make it clearer, or you can go through and change the labels on the graphs. Baldness is a disease. And then baldness treatment should be funded. So if I want to go through, and chart this, I do have a problem in that all of these are listed as numbers, and Minitab doesn't have the facility to add labels to it the way SPSS does. As far as I'm aware, if anyone has a way of doing this, let me know. So either you can go through and recode all of this as labels, which is not actually that time consuming. So you would go to data, code, and change from numeric to text, and then you just need to go through and type in. You can see that I've already done this for the group, where I went from group, store it in a new column just so I don't lose my original data. And if it's 1, call it lay people, if it's 2, call it doctors, etc. Or we can go through on the graph and add in some labels when we're happy with it. So let's do that. If we go to bar chart, and I'm after a clustered bar chart because I want to have a look at 2 variables together. The 2 variables I want to look at are the different groups of people, so by their profession, whether or not they're lay people, doctors, nurses or members of parliament, and then I want to know whether or not they classified baldness as a disease. So that's that variable there. Just go through some of these options. Now what I would like to know is, if we just do it, let's see, if I'm going to untick that for now and just show you the graph as it would come out, and then we'll come back and have a look at that. Cancel labels, and again I want to take that out for now. Data view, I'm going to leave this in because otherwise it won't come up with the colors, but I'll show you where that is. Multiple graphs, you can leave that, and data options. Now by default you may see that under data options, group options, it says include the missing as a group. Now you might want to do this the first time you do a table just to see how much missing data you have. Possibly you won't always want this in there, and I'm just going to leave that unchecked for the moment. I don't want to include those just right now, and click OK. So now we can see that within doctors, lay people, members of parliament, nurses, how many agreed with baldness being a disease, from strongly disagree to strongly agree with number 5. Now the difficulty we have here is that they actually got a lot more lay people to respond to the survey than all the other groups, and they had very few members of parliament respond. And so it's a little bit difficult to compare the percentage of lay people who strongly disagreed with baldness being disease as compared with, say, doctors, members of parliament or nurses, because the sample sizes are so different. So what I really want to do is chart these as a percentage. So I'm going to go back into my graph, bar chart clustered. I want to show Y as a percent. Now I would actually like a little bit more flexibility in which order I was plotting these, and if you have a look in the notes for the way SPSS does it, it actually does give you more options, and so this is one of the few times where SPSS just actually does a better job than Minitab for looking at this type of thing. So I'm going to click OK, and that's going to show Y as a percent within each category at level 1. Scale, that's fine. If you want any of your charts to go across rather than up and down, you can click this transpose. Transpose just means switch it around, and that's really just a personal preference. Group options, we already had a look at that. Data view. So the fact that it's showing each group of people as a different color is due to using this categorical variable for attribute assignment. If I took group name out of there and put baldness as a disease in there instead, it would color it by how much they agreed with the statement that baldness is a disease, the 1s, 2s, 3s, 4s and 5s. So we could try that. Okay. Now the other thing we might want to do, this graph is looking better now. The other thing we might want to do is just add some more helpful labels to this 1, 2, 3, 4 and 5. If you double click on anything, it should bring you up a box to modify it. And in the labels here, I actually don't want, I'd prefer not to have really long labels. So what I'm going to write is strongly disagree, disagree, neither agree nor disagree, agree, and strongly agree. So they're quite a bit brief, perhaps a bit too brief, but more helpful than before. So now it's a little bit easier to pick out interesting features of the data set. So we can see the percentage. If I look within people who strongly disagree, if I look at all the red ones, people who strongly disagree with baldness being a disease, we can see that the highest percentage is the doctors, dropping down for the members of parliament. They're less likely to feel quite so strongly. However, there is a lot greater percentage of members of parliament who just disagreed. So they still disagreed with baldness being a disease, but they weren't so strong in their opinions. They weren't going to strongly disagree. And it's possible that politicians, I don't know, that are less likely to strongly disagree with anything because they're always conscious of offending people. So it's possible that this is a pattern of members of parliament, and you'd have to look into the data set a bit more to have a look at that. And now we can see some other interesting patterns here. So you can see there's a big difference here in the doctors agreeing and strongly agreeing with baldness being a disease as compared with the other groups. Now to test to see if these differences between how these groups react to this question, so the null hypothesis would be, null hypothesis is that there is no association between your profession and your view on baldness being a disease. The alternative is that there is an association. And the test we're going to have a look at is the chi-squared test, which is fairly quick. If we go to stat, tables, and you've got a few options here, we want to have a look at a cross tabulation and chi-square. And I'll drag this across. In the worksheet I've used group name for the row, but mathematically the test is the same either way around. It's just really a matter of convenience as to which one is easier to look at. For columns I've renamed that, so I'll have to go and double click that, baldness is a disease. And I would like to see the counts, how many people are in each cell. For my test I do want to see the chi-square analysis. I would also like to see the expected cell counts, and I would also like to see the standardized residuals. You can pick some of these other ones if you want to, but this is all I'm going to look at for now. If you display all of them, it does get a little bit messy. Other stats, let's have a look. We're not going to do any of these at the moment. Cancel options. And this is where, at the moment, it's not. I can't remember what the default is, whether it's going to include the missing values or not. If you get an extra category coming up with missing data in it, you can turn that off if you want to here. Okay. So we get a warning at the bottom that 2 cells have an expected cell count of less than 5. Now this may mean that the test is not working as expected, and so you need to be careful if you've got a lot of low expected cell counts. In this case it's probably okay, and it's due to the members of parliament. I don't believe they got a very good response rate, although 57 in total. I would have thought that might even be better than they expected, to get 57 politicians respond to you. So just to explain the numbers that we've got here, the top number is the observed value. So these are the people that actually responded on the survey in each group. So these are the counted up values. And that's why we've got a different number in each category, because they got different numbers of people responding to the survey. The biggest group of responders were the lay people, the nurses, then the doctors, and lastly the members of parliament. But I think they asked fewer. I don't think there are quite so many members of parliament to ask. You'd have to go back to the original paper to find out how many they asked of each group. Now the next cell here is the expected cell count. So that means, under the null hypothesis, if there is no relationship between your profession and whether or not you think baldness is a disease, then this is the number of people we would have expected to find in each group here. And the difference between what we expect to see and what we actually see is what gives us our value for whether or not we've got evidence against the null hypothesis. Now the standardized residual, which is the third row in each cell, is a measure of how far away our expected value, our observed value, is from our expected value. Now you can see here with the doctors that if being a doctor had no impact on whether or not you thought baldness was a disease, we would have expected to see almost 22 people in this group, and actually we've only got 5, and that's a pretty big difference. And so we've got a large standardized residual. And the reason for using the standardized residuals is that it makes it easier to compare. So if there was no difference between what we expected to see and what we actually saw, then the residual, or the bit left over, would be about 0. Anything that's far away from 0, either positive or negative, is a large value. And by far away from 0, I would mean 2 or 3, so it's not that big. So anything that's -2, -3, or +2, +3, I would consider to be a large standardized residual, and it's having an impact on the results. So in this case we can see we had a lot fewer doctors than expected who strongly agreed with baldness being a disease, and also a lot fewer doctors than expected who just agreed with baldness being a disease. And we can have a look through to see if there's any other large residuals. So there's a big one here, so with our 2.2. So this is members of parliament who disagreed with baldness being a disease. Now the actual test is given down here. The test statistic is 48, and I know that's quite large because if you've ever worked through the test by hand, you get a feeling for which are large and small values. And we have a p-value of 0.000. So the null hypothesis is that there is no association between this group of professions and classifying baldness as a disease. We have very strong evidence against the null hypothesis, and therefore there is some association between your profession and classifying baldness as a disease. That's all the test will tell you. To work out what that difference is, you have to go through and have a look at these differences between the observed and the expected, and then you would probably refer back to a graph, just because the graphs are they make it easier to visualize what's going on. So the biggest difference we've got is the doctors who don't classify baldness as a disease. And what's interesting to me is that we don't see the same effect with nurses. So we've got two different medical professions. Obviously doctors have a very different training from nurses, and they are also much less likely to classify baldness as a disease. So that's an interesting difference there. Now, the other question that they asked about each condition is not only is this condition a disease, but should treatment for the condition be publicly funded out of tax money? So if we go and have a look at that, I'll do a cluster chart again, and instead of looking at is baldness a disease, let's have a look at should the treatment be publicly funded? That's because I had that. I need to change that over as well. So just remembering that the 1 is the strongly disagree and the 5 is the strongly agree. So we can see that the doctors do not agree with baldness treatment being publicly funded. In fact, very few people do. Now, what would be interesting to me is that if you have already agreed that baldness is a disease, do you then think that are you then more likely to think that it should be publicly funded? So rather than grouped by your profession, I would like to see it grouped by what you answered to the first question. So if I come back into the graph here, and instead of group, I want to see what your answer was to the first question. Is it a disease? And then based on whether you thought it was a disease, do you think it should be publicly funded? And this is quite an interesting graph. So if we read through this slowly, and we've got a little bit of if you were putting this graph in a report, you really need to change these labels because they're not user-friendly. If I change just baldness is a disease, so strongly disagree, disagree, neutral agree, strongly agree. So the people who strongly disagreed with baldness being a disease, also nearly up to 100% of them thought that it should not be publicly funded. Then if we look at the other end of the spectrum, the people who strongly agreed that baldness was a disease, we can see that they split. Even if they agreed that baldness was a disease, they did not necessarily think that it should be publicly funded. So we've got within this group here, the ones strongly disagreed with it being publicly funded. So you can see that within each person there's a difference here, that just because you classify something as a disease does not mean that you automatically think that it should get public funding. And it's interesting to contrast this to some of the other conditions, say one like autism, because there's also a big split over whether people think autism should be classed as a disease, but they go the other way on whether or not the treatment should be funded. So if we have a quick look at that clustered bar chart, now I'm going to take out the baldness and we're going to add in, if I scroll down, there's a lot here that you can look at, autism A and autism B. So A is whether or not you think it's a disease, and B is if it should be publicly funded. Okay, where are the labels? Not there. This one. Should it be publicly funded? That's the B. And what we see here is the opposite pattern. So out of the people that strongly agreed that autism was a disease, they also, on the whole, strongly agreed that it should be publicly funded, up close to 90%. Not absolutely everyone, but a good, a very, very high proportion of them. Whereas at the other end of the spectrum, we've got this split, whereas these are the people who strongly disagree that autism is a disease. But out of the people that strongly disagree that it's a disease, we see that nearly 40% of them, and if we added on that 10% too for the agrees and strongly agrees, over 50% of them agree that it should be publicly funded. So even though they don't believe it's a disease, they do believe it should be publicly funded. The treatment should be, and that's quite interesting. So this kind of data set, I think, is very, very interesting if you're involved in any kind of funding or policy decisions. I think it was from a Scandinavian country. You have to look back at the paper, so it'd be really interesting to see some of this redone in Australia or other countries, just to compare and contrast the results. And of course you can go through and do the chi-squared test. However, the chi-square test is really just telling you if there is an association or not between your profession and classifying it as a disease. And when you've got really big numbers, often you can tell without running the test that there is an association. And sometimes what's more interesting is the patterns of what's going on in between, such as this pattern here with the autism. And if you put them side by side, you can see that you're getting this opposite pattern from autism to baldness. So if you're doing these, you may need to play around with the graphs a little bit just to get them the way you want, add some labels in, and these tables you can cut and paste into Excel so that you can format them more nicely. They're not friendly the way that they are. Just all of this stuff you can just select, Control C, and paste it into Excel. Now if it tries to put it all in the one cell, you might want to use the import wizard just to make it split it up. And you can see where it's going to put the columns there. That's better. So now you can go through and format that before you put it in a report.